All right, so we'll be growing some crystals today in TouchDesigner, some snow crystals to be exact, using only tops, so no coding required for this one, so it should be fairly beginner friendly. And this setup is inspired by Entagma's video on procedural snowflakes in Houdini, which itself is based off of a paper by Clifford A. Reiter. I'll link both of them down in the description, so check them out. And basically what we have to do here, if I pause this, is we start out with a grid, a hexagonal grid with a initial value. I'm going with 0.4 here. So this represents our vapor field. Inside of our vapor field, we will be adding a frozen seed. You can go with more frozen seeds here, but important to note, everything that has a value of over 1 or equal to 1 means that it is frozen, and everything that is below 1 means that it is still in a water vapor state. So we add a singular seed here in the center, give it a value of, let's say, 1.1. And for the next step, we calculate, or we select the neighbors of every frozen cell. We have these 6 neighbors. We select them and we separate it out into 2 streams. One is the receptive cells up here, every frozen cell and its neighbors. And to that, we just add a constant value. In this case, I added 0.1 here, but that is also a parameter we can change. So 0.4 goes to 0.5, 1.1 goes to 1.2. That's basically it for that. And a bit more complicated part here is the non-receptive cells. We take this entire field and we fill in the receptive cells with 0.0 here. So every frozen cell, again, every frozen cell and its neighbor or neighbors gets a value of 0.0. And we do this weighted diffusion on every cell. What this does is we take this scope basically, or this multiplication matrix, and we go over each cell. So we line the center one, starting with this cell here. We multiply the value with 0.5 and we multiply every neighbor with 112. And then at the end, we add up all the values and that becomes the new value of this cell. So it might look like that we are changing the values of these cells here as well, but these don't change. When we are processing this cell up here, we're just multiplying this one by 112, 112, and these one here in theory as well. And then we add them all up together. And as you can see here, adding the coefficients up here returns 1. So 0.5 plus all these values equals to 1. And when we are in these areas where everything's 0.4, nothing's going to change. But as soon as we have different values here, let's say we line up to this one or this one, you can see 112 times 0 is 0. This is 0. This is 0.2. So 1/2 times 0.4 is 0.2. And then 4 of these 0.4s, which is 1.6 divided by 12, is 0.13333, I believe. So this cell then gets a value of 0.2 plus 0.133. And that's 1/3. And if we are up here, we could see this returns 0, 0, 0. And these 3, so 3 times 0.4 is 1.2 divided by 12 is 0.1. And this cell is 0. Adding them all together returns that this field then turns to 0.1. And then we have this diffused field here with the new values. And the final step, we just add these to these again, and we get this second frame. And the most important step, this new frame then gets fed back to this step here, where we again select all the neighbors of the frozen cells. Right now, it's still only the singular cell here that is frozen, but as the value increases, we will get more frozen cells and it's going to grow out beautifully. So let's build this in TouchDesigner. Let's just delete everything here and start anew. So let's start out with our field. We'll do that with a constant and we fill it in with 0.4. And let's set the pixel format to 32-bit float mono. Viewer smoothness has to be nearest pixel for every one of these. And resolution, let's just go with the low resolution for now so we can kind of see what's going on. And that's basically it for our field. So let's add our frozen seed here, which is 1 by 1 pixel. Also nearest pixel, also 32-bit float, set this to nearest pixel as well. If you don't want to set it every time, you can change the preference here in preferences, tops. Under default viewer smoothness, you can change this. I believe the default is interpolate pixels. You can change this to nearest pixel. Just remember that you changed the setting though, so you don't run into any issues later on. And let's set this value to 1.1 Oops, these can be 0. They don't matter because we're just using 32-bit float mono. And to put these two together, let's just use a comp. And we have to, in the transform, set prefit overlay to native resolution. So it gets the 1:1 resolution here and 31 by 31. We're using an odd number here so that we can have a perfectly centered pixel. So instead of multiply, let's do brightest. So it checks for each pixel which pixel is brightest. And we have this beautiful field with, oops, let's activate this. You can see that everything is 0.4 and the center is 1.1. Just call this our starting field. And that's basically it. So this step is done. Let's select the neighbors of the frozen cells. And this entire thing is a feedback loop. And this is the first step of our feedback loop. So we have to put this step, since we have to find the neighbors of the frozen cells for each new frame that comes in, we have to put that into our feedback loop instead of outside of it. So let's add a feedback here, and always good practice to just immediately drop in the keyboard in. Let's chop reference it to the feedback reset thing here. And just to tidy it up, we can right click dock tool, and now it is under here. So we need to select the neighbors of the frozen cells. So to find the neighbors of the frozen cells, we have to first find the frozen cells themselves. That twisted my tongue. Okay, so everything that is under 1 is not frozen, so comparator less than 1. And what this threshold returns is a value of either 0, which is all of this, everything that is less than 1, and everything that's more or equal to 1 gets a value of 1. So important to note is that we're not using the values from here. This is just a mask, so to say. We can see that the value here is 1.1 in the center, and this turns into a 1. So this is either just yes, it is more than 1 or equal, or it is less than 1, and it decides either it's black or white. We're not using the values here, we're just creating a new mask, so to say. So let's call this the frozen mask. And using this frozen mask or the frozen selection here, we can find the neighbors of this. So let's use a convolve here, or a convolve. And we run into the first major issue that we have, which is that we don't have hexagonal pixels. You might have noticed this earlier, but pixels don't look like this. Pixels are square. We could use pops to kind of like create this hexagonal grid and then instance points or instance geometry onto it and render it out with, I don't know, point attributes. But at that point, we might as well just do Entagma's tutorial in Houdini. So we kind of have to cheat a little bit. And what I want to do is, instead of selecting all the neighbors, since, let me do that here. Every square pixel has 8 neighbors. So 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7, 8. There we go. Instead of selecting all of these, which would create like a octagonal snowflake, I'm just going to select these 3 on the top right and these 3 in the bottom left, and then kind of like skew the image later on. It's a bit of a cheat, but it works pretty well. So I'm going to select these 3 and these 3, and using the convolve, what this convolve does is we get this little multiplication coefficient matrix here, which looks a bit similar to what we have here, right? So we have a center value, and that right now is 5 by default. We have values for every pixel around it. What this does, it lines up the center value to whichever pixel is being processed. So let's say this one multiplies that by 5, which is 0, multiplies that by -1, which is 0, this by -1, this by -1, and this by 1, adds them all together, which returns 0 because nothing is there. And the center value that we have here is 1, and right here we have 5, because when this coefficient, or this convolve, sorry, is processing this pixel, it multiplies itself by 5, which returns 5, and the neighbors all by these values, which in addition to each other is still 0. So we get a 5 here. And you might say, but the right pixel is lit up even though the left one here is the only one that has a positive value. That's because we're not changing the neighbors here. We're changing the pixel that is being processed based off of the neighbors. So when the convolve hits this pixel, hits the second pixel here, it multiplies that by 5, which is 0, and the left pixel by positive 1. So the pixel to the left of this one is 1, so that is 1, and everything else is 0. So we get a 1 here, and the left one gets a negative 1 because the pixel to the right is positive here. So negative 1 by 1 gives negative 1. Hope that makes sense. So let's select neighbors here. For every pixel, I want to grab the top right. We're just using 1 here because it's a mask. It's either 1 or 0. There we go. So 1, 1, 1, 1, 1. And we kind of have the neighbors here selected, the top right and the bottom left. One thing to note is because it's adding these all together, right now we only have a singular pixel. But if we were to have more here or later on when the simulation goes on, let's press 1 to reset the feedback loop. We can see that the values go up to 7 here, which is going to destroy our mask. This should be either 1 or 0 because we'll be using this to multiply with this image so we can kind of mask it out. So let's clamp it down to 0 to 1 with the level. Let's do clamp 0 to 1 and let's call this neighbors selection. And this is going to be our receptive mask, and we can hide the table with this one. So let's multiply the mask with the input image so we get the masked image. So we'll use a select here because it's going to get super messy if we wire it up directly. So the starting frame of our feedback multiplied by our receptive mask returns the receptive cells here. Let's hit 1 again so we reset the feedback loop. So we got a singular pixel in the center of value 1.1. The neighbors, which are 0.4, and everything else is 0. And let's do the same with the non-receptive cells. Let me just copy the select here. And we have to invert this mask because we want to select everything else. So wait, let me just check one thing before I do that. Can I divide this? No, I cannot. Okay, don't believe anything I'm saying. Let's use a level and invert our mask. I don't know why I even tried dividing it. So, same setup as this here. Let's use our inverted mask, move it over a bit here so it's clean, and multiply these two, and we get all the values around our receptive cells. So everything is 0.4 and the center is filled with zeros, exactly how we want it here. So the receptive cells, we will add a constant value. And if we do this after this, you can see that it's brightening up the whole image, but we only want the center part to be brightened up. So what we can do here is just to add before we mask it out, because the 0.4s here are getting masked out anyways. So let's go 0.001, a bit of a smaller value. Let's delete that. And you can see in here, everything has more than before, and these are still 0. And in here, what we have to do is this operation. So we can use another convolve here and fill these cells with 112. And just to make sure what 112 even is, 0.083, oops, 3. So let's just paste that in here. There we go, and the center was 0.5. I get this kind of blurred image here, and that's basically it. Final step, we add these together. Let's put that here maybe, and we just put the final frame after our process here back into our feedback and hit play. You can see that we're growing a flower here. So just a sanity check, let's select all of these and select nearest pixel so we don't get any issues. For our final step, let's skew or unskew the image with the displace, and we can use a ramp for this. Set the ramp to vertical and plug it into the second input of the displace. And vertical source, let's do none, and displace weight, I think 0.25. So let's hit 1 again and see it's kind of growing out. It's crazy how nature is like this mathematical and simple. honestly. Okay, without getting too philosophical here, let's use a threshold to kind of mask out the ice again. So we only get the ice in the final image. And in our constant, we can up the resolution here. So let's do 1024 maybe. You can do 1025 so you get a centered image. And you can see it's kind of slowly growing out. And one more thing you can do is add a noise here. So let's do a comp here and let's add a noise. We're using this input here so we can get the resolution, but we have to set output to only noise, and in the noise, let's set that to random. And let's also create a constant chop so we have these parameters so we can change. So first of all, we will do vapor temp. I guess it's not really the vapor temp, it's more like frozenness of the vapor because, you know, temperature, the colder it gets, I don't know what I'm talking about. So let's do second is seed temp. So this was set to 1.1 and one more for addition. I think the paper called these like alpha, beta, and gamma, but I'm using English here. I'm not using Greek. By the way, funny thing, someone said that my name in Greek meant and I was considering changing my name because of that. So I'm not sure if I should. Maybe if like more than 5% of my viewers are Greek, I'll change my name, but until then, it will have to be. It took so long to find a name that wasn't already taken. Anyways, so variance seed. So on the seed, let's 1, 2, 3, 4, 5. Variance, maybe 0.2. And the addition was what, 0.001. And the variance, let's also plug this up to here, by the way. And the variance, what this does is we can just put that on our noise. The amplitude, basically. So how big the noise should be, or how variant the noise should be, and the offset, let's set that to 1. So here we should have values between 0.3 and 0.5, I believe, because this is 0.2 and it's going up by 0.1 and down by 0.1. And let's just do everything else as well. So the starting vapor temp and the seed temp and the addition right here. What else? I think that was it, right? Okay, so we have this control thing here that we can use to control what our snowflake looks like. And if you have at a certain frame a look that you like, we can use a cache, just like that Counter-Strike map where let's just disable this and enable this, where you can just turn off the active and use a prefill, maybe cache size to 1. And you can just kind of like cache the frame that you want. So let's do a second one here. Let's maybe do that. That's pretty nice. And let's see, what if this is like super high and this is 0 and this is maybe 0.05. Oops, I destroyed everything again. You can see it's kind of like this fractal snowflake thing. So that looks pretty nice. And maybe one more, maybe 7.5 here, maybe 0.02 here. What does that look like? Let's put that in here. It's growing very fast. But yeah, you can get some pretty nice looking snowflakes here. So yeah, play around with these values, maybe add some noise here, maybe add some more constants or some more seeds. Let's actually do that right now. Let's set this back to 0.4. We have time for this. So let's 0.001, maybe 0.1 in variance. So let's do that. Okay, let's see what happens here. What happens if I add like a noise here and I do threshold? And this is random, maybe not random. So you kind of have these spots. Okay, that should work fine, I think. What is the resolution here, by the way? Let me use this resolution. Only noise, and let's put that in. Okay, so this is not really working that well because we're displacing it here, so maybe mirror. You can get these nice ice crystals. These many ice crystals growing here. Looks pretty fun. And you can do anything with this. You could maybe do some ASCII art with this, where you instance on every pixel a letter. Because right now it's looking pretty pixelated because we're literally working on a pixel level here. So yeah, tweak the settings, do what you like, and let me know what you think. If you have any questions, I'll do my best down there to help you out. And leave a like, subscribe, and I'll see you in the next one. Cheers.